All right. Hi, and welcome to video 3 of 3 for chapter 3. In the previous two videos, we looked at the first law of thermodynamics and what it implied with respect to changes in internal energy and the different types of work that you could see done. Now, today, I'm going to finish up our discussion by talking about something called an adiabatic process. So, an adiabatic process is one that has no energy in or energy out of the system during the state change. Okay. So, what we say is that the energy within the system is conserved over a short period of time. Now, this is a pretty big deal. In many cases, when it comes to real world phenomena, what we like to do is to try to set them up in an adiabatic manner so we can invoke things like conservation of energy. So, if you think about the first law of thermodynamics, which says that when you add heat, you have the potential to change the internal energy and also cause work to be done to the environment. When you say that the energy within the system itself is conserved, what that means is that you're not adding heat or letting any heat out, basically. So adiabatic processes are ones in which dq is equal to zero. Now, when I say that this occurs over a short period of time, there's a reason for that. And that's because um, if you think about the description of thermodynamics that we've talked about in the past, where you have the system like this, like an ice chest, like we talked about in the first video, and the environment. At the boundary, you have an exchange of heat. Remember, when we talked about heat transport, anything in nature that has a temperature is going to radiate energy. So you always have that potential for energy loss into the environment. But if you take a short enough time period, then it's possible to keep the energy within your system more or less conserved. Now, that said, I would like to talk briefly about reversibility in things. So, when we talk about a process, what we mean is that you take your gas from, we'll say, one state to another state. Okay. Now, because of how complicated thermodynamic processes are, in reality, in nature, we say that processes are not reversible. Now, what do I mean by this? Well, okay. Um, let's pick a simple example. You go to, I don't know, make breakfast in the morning. You grab your bowl out of, the cupboard. You get some milk. You get some cereal. You put the cereal in the bowl. You put the milk in the bowl. You grab a spoon and you go to town. So let's think about that up to the point to right before you start to take your first bite of your cereal. You've added milk into the cereal. You've gotten your bowl and you have your spoon. Now, how would you reverse that? How would you take and put everything back to how it was before in exactly the same manner that it took to get there? Well, you would have to somehow be able to completely and exactly retrace your steps to putting the bowl back exactly as how you took it out, the spoon back exactly as to how you took it out, the cereal back into the box in the same manner and order in which all the bits of cereal tumbled out. They would have to go back in reversibly. And also, somehow, since you've poured the milk onto the cereal, you would have to be able to get the milk back into the bottle in exactly the same manner and order the milk molecules came out. So as you can see, because of the fact that things are made out of atoms and molecules, and they're incredibly complicated systems, in reality, nothing really is reversible. But we can say on a short enough time scale, things can be reversible. And there are adiabatic processes that, taken in very small increments, infinitesimal increments, you can walk backwards. Now, so processes that are both adiabatic and are reversible, or very close to being reversible, we say are isentropic. Now, this will make more sense when we talk about entropy in the next few chapters. Okay, so here's the deal. Adiabatic processes are defined by a state change that goes from one to another state, but doesn't allow any energy in or out. And if you can actually reverse that process, not only is it adiabatic, but we say that it's also isentropic. Okay, so in the list of stuff where you have, isovolumetric U expansion or isovolumetric state changes, where you have isothermal, where you have isobaric. Now we have adiabatic and isentropic. Okay. So that said, let's talk about how you deal with adiabatic stuff and what that means. So what I'd like to do is to examine adiabatic processes. And I want to show you how they can be used to talk about how more than just two of our macroscopic observables or variables can sort of operate at the same time. Now, what do I mean by that? Well, if you think about the ideal gas law, PV is equal to nRT, we generally assume, at least for the time being, that the number of moles or the number of atoms is held fixed. And then what we do is we fix one of these other variables. We say it's isothermal, which holds this fixed, or it's isovolumetric, which holds this fixed, or it's isobaric, which holds this fixed. And what that does is to allow us to examine the behavior of just two of these things. Okay. Now, when you have a third one at play doing its thing, you can't stop with just the ideal gas law, because now instead of having a clear relationship between two variables, you have the third one in the mix, and you need an extra set of equations or an extra set of boundary conditions in order to understand and explain this behavior. And in part, that's where adiabatic stuff comes in. So if you think about, again, the first law of thermodynamics, like this, and then you say, okay, what I want to do is I want to look at the relationships of these things, but I'm not going to hold really anything fixed other than just letting no heat come in and no heat go out. Okay. So we know du, which is your internal energy, you can write as 3/2 nr dt. Or you can take the approach that we took towards the end of the last video and write this in terms of the molar specific heat at constant volume. So this would be the same thing as C sub V in dt. Likewise, if you look at work, we can write as P times dV. So what I have here is using the first law, 0, no heat in, no heat out, is equal to C sub V times N dt plus P times dV. Now, what I'd like to do is to take this and rewrite this in terms of ideal gas law. So pressure, we know, is nRT over V, which means that I can write this as C sub V times N times dt plus nRT over V dV. Now, this is equal to 0. I'm going to cancel out the number of moles. It doesn't matter anymore. And what you're left with is an equation that looks like this. C sub V times dt plus RT over V times dV is equal to 0. So what I'm going to do now is to rewrite this RT over V just a little bit. And to do that, I'd like to remind you about the relationship between the molar specific heat at constant pressure, the molar specific heat at constant volume, and the ideal gas constant. So I can write R as the difference between these two, which is exactly what I want to do. All right. Now, I'm going to divide both sides by CV. I'm also going to divide both sides by T. And when I do that, I have dt over T plus Cp minus Cv over Cv times dV over V is equal to 0. Now, we define conventionally Cp over Cv as something called gamma. Inside gamma, you have information about the number of degrees of freedom. And I'm going to show you a few gammas here in a little bit, just to give you a sense of how this works. Now, that said, I can rewrite this as dt over T plus gamma minus 1 dV over V is equal to 0. Now, what I'm going to do is to take this right here and move this to the right-hand side. I have dt over T on the left-hand side. On the right-hand side, I have gamma minus 1, so minus sign out in front, dV over V. Okay? Now, what I'm going to do is to integrate both sides. But I'm going to do an indefinite integral because I don't know what my initial and final temperatures might be in an adiabatic situation. That would be something that perhaps I would be given. And I don't know what my initial and my final volumes are. So I'm going to do an indefinite integral. Left-hand side is just dt over T. Right-hand side is minus gamma minus 1 integral of dV over V. I take my integral. On the left-hand side, this is the natural log of the temperature plus a constant that I'll call C1. On the right-hand side, I have a minus gamma minus 1 times the natural log of the volume plus a constant that I'll call C2. Now, do I want to do this like this? Yes, I do. Okay. So, what I want to do now is to move this to the left-hand side and move this to the right-hand side. I'd have natural log of T plus gamma minus 1 natural log of V on the left-hand side. On the right-hand side, I have C2 minus C1. Now, this is just a constant, which I'm going to call, I don't know, C3. That sounds good. Okay, so if you take a look here, I have on the left-hand side what looks like the sum of two natural logs. I'm going to pull this into one by taking and moving this right here using the rules of logarithms onto the volume, like that. Now I can pull this into this. Now, the next thing I'm going to do is to take and raise e to the power of both sides. When I do that, on the left-hand side, I get t times v to the gamma minus 1. And on the right-hand side, I get e to the c cubed. This is just a constant. I'll call it C4. Just constants. Those are things that eventually you solve for whenever you have your conditions that allow you to find them. Okay? So basically what you have here is that in an adiabatic process, T times V to the gamma minus 1 is constant. Now there are some other relationships here too. You can use the ideal gas law to solve for them. For example, what if I took and I looked, instead of temperature, I looked at pressure? Well, temperature is equal to PV over NR. I'm going to put that in here. So this V hits this, and since this is V to the first power and the minus first power kill each other off. N and R are assumed to be constants. R we know is a constant. N is the number of moles, which, like I told you, really doesn't change unless you're explicitly told. If you're explicitly told, then things are off a little bit. This is constant. So I'm just moving it to the right-hand side. Just, it's a constant. So I have that T times V to the gamma minus 1 is constant. P times V to the gamma is constant. You can also find relationships if you want between T and P. We're not going to do that here, but that's going to be an exercise that's left up to the student, if you will. So what this allows us to do is to use the ideal gas law. If you look up over here, for example, where I talked about how I think it was right here actually, where I talked about how typically you hold two of these things fixed, but what if you have three? So now you have this right here that you can work with. And then you can use these two, if you'd like, to add in an extra equation that allows you to actually work within, your problem, if you will. You have enough information. So now you have basically two equations and three unknowns, potentially no unknowns if you have the right initial and final conditions. So just as an example, a living habitat on Mars that's pressurized to 1 atmosphere of pressure is holed by a meteorite, venting 100 cubic meters of air into the Martian atmosphere before it's sealed. If the initial temperature of the air is 305 Kelvin and the Martian atmosphere has a pressure of 600 pascals, what volume does the vented air expand to? What is its final temperature? Now, we are going to assume that this happens very quickly, and as a consequence, there is no loss of heat into the environment. There's no exchange of energy between the air itself and in the Martian atmosphere, if you will. Now, obviously, over a longer time scale, there definitely is, but on a short enough time scale, there isn't. So what are we given here? Our initial pressure, which I'll call P1, is 1 atmosphere. 1 atmosphere is 1.01 times 10 to the 5th pascals. My initial volume, which I'm going to call V1, is 100.0 cubic meters. The initial temperature of my air, which I'll call T1, is 305 Kelvin. I also know my new pressure. That is 600 pascals. Now I'm trying to find my new volume and also my new temperature. Okay. What I do know is that since it's adiabatic, if I know what kind of gas I'm dealing with, this combination of temperature and volume is constant, and this combination of pressure and volume is constant. So now let's not forget the gamma itself is the specific heat, the molar specific heat at constant pressure of your gas divided by the molar specific heat at constant volume. Now, so before we get grinding into this problem, which is actually a pretty easy problem to do, let's talk about the differences in specific heats here. So you have three basic types of gases. Monatomic, meaning that you have one atom in your molecule of gas, if you will. Diatomic, which is two. And polyatomic, which is more, but we can model using just 2 additional degrees of freedom. So if you look at the specific heats at constant pressure and you look at the specific heats at constant volume, keeping in mind that the specific heat at constant volume is d over 2 times r, and the relationship between Cp and Cv is that Cp is equal to Cv minus r, or plus r, right? Plus r? Yeah, minus. No, plus. That's right. There we go. Plus. All right. So for a monatomic one, the number of degrees of freedom are 3. We've mentioned this before. So Cv would be 3 halves times r. Cp is going to be an additional r to that, which would be 5 halves. For a diatomic gas, what we say is that your gas can vibrate, and then it can also rotate, which gives you 2 additional degrees of freedom. So in that case, instead of this being 3, it would be 5 halves. This is going to be 7 halves. With a polyatomic, it can do all sorts of things. Like that. Now, so I'm going to treat this gas like it's a diatomic one. All right. What that means is that my gamma in this case, which would be Cp over Cv, would be 7 halves r over 5 halves r. The halves cancel, the r's cancel, meaning that this is 7/5. So my gamma in this problem is 7/5. So I know, according to adiabatic processes, that P1 V1 to the gamma is going to equal to P2 V2 to the gamma because it's constant. So P1 V1 to the 7/5 is equal to P2 V2 to the 7/5. Now, I'm trying to find V2 and T2. I'm going to use this to find V2. So what I have here is that V2 to the 7/5 is equal to P1 over P2 times V1 to the 7/5. Now I'll raise it to the 5/7 power on both sides. Okay, if I do that and I let this go through, this 5/7 is going to hit this and make it be a 1, and it's going to put a 5/7 on the P1 over P2. Times V1. So there you go. There's your relationship between the two. Now, so V1 here then is going, or V2 rather, V2 is going to equal to V1, which is 100.0 cubic meters, times P1 over P2 to the 5/7 power. That's going to be 1.01 times 10 to the 5th pascals divided by 600 pascals raised to the 5/7. Now, if I put this in my calculator, I have 100 times 1.01 times 10 to the 5th divided by 600. And then I'm going to raise that to the 5/7 power. And I get 3,891. If you round, about 3,892 cubic meters. So it's going to expand tremendously. And it expands tremendously because of the fact that it's expanding into such a low pressure environment. Now, what about the temperature? Well, we can apply this right here to get the temperature. Or we could use the ideal gas law. It doesn't matter. So let's just use this to be consistent. T times V to the gamma minus 1. So T1 V1 to the gamma minus 1 would equal to T2 V2 to the gamma minus 1. Now remember, gamma is 7/5. So 7/5 minus 1 would be 5/5. This would be the same thing as 2/5. Okay? So this would be T1 V1 to the 2/5 is equal to T2 V2 to the 2/5. We're looking for T2. So I'm going to divide both sides by V2 to the 2/5. And then I'm going to go ahead and just pull the V's into each other like that, because that's just the 2/5 power. Now, my initial temperature was 305 Kelvin. My initial volume was 100 cubic meters. And my new volume is 3,892 cubic meters. And then I have to raise that to the 2/5 power. So if I do that, 305 times 100 divided by 3,892 raised to the 2/5, you get 70.5 Kelvin. So what's happened here is that your gas expanded into this low pressure area. And as a consequence, the temperature dropped really, really far down. Now, this should make sense. If you take a look at the first law of thermodynamics, in an adiabatic situation. So remember, the first law says dq is equal to du plus dw. But if dq is equal to 0, what you have is this relationship right here between the work that's done by the gas and the internal energy. Basically, what this means is that if you want your gas to do any work, that energy has to come from inside the gas. It comes from the motions of the atoms and molecules that make the gas up. So here, because this expands out into this low pressure environment, it's doing work on the environment. So you end up with this tremendous amount of work being done because of the expansion. And that comes at a cost of temperature because that energy has to come from somewhere. So that's basically what's going on here. Now, what I'd like to point out here is that we were able to work not just with pressure and volume changing, or temperature and volume changing, but both pressure, temperature, and volume all changing simultaneously. So you're able to work with more than just two variables in your state equation, which, if you can set things up in an adiabatic situation, is definitely the way to go. All right, so that's it for this video, and I will see you in Chapter 4.